Okay, good afternoon. The first speaker after lunch, we're going to have Jonathan Hurst as our first speaker. Jonathan Hurst is a professor of robotics at Oregon State University and co-founder of the OSU Robotics Institute and chief technology officer and co-founder of Agility Robotics. He earned his bachelor's in mechanical engineering and his master's and PhD in robotics from Carnegie Mellon University. And his research focuses on the science and engineering of locomotion, combining numerical analysis, animal data, simulation, and robot experiments to study walking and running. At Agility Robotics, this research is being extended to commercial applications of legged mobility, working toward robots that can go where people go and enhance productivity and quality of life.
Thank you. So I'm going to talk today about manipulation and locomotion and the differences that I see between them. My background started with locomotion, and there's a lot of tools that we used that worked quite well to make robots that could walk and run. But it turns out that manipulation is fundamentally different in a few interesting ways. So as I give this talk, I would appreciate some questions or comments or thoughts anytime. So, raise your hand or button in the middle. And honestly, it's okay if I don't get through the whole presentation. We can stop and then just talk about whatever the interesting points are. So please, informal. It's a nice small room here. Okay. So to start, I'll point out what I said also in the industry forum at the conference on robot learning, the overlap day. Model-based control is obsolete. There are a couple of basic reasons. Number one is it requires that on your robot in real time, you're simulating forward a bunch of different, things to try to figure out which is the right path to take, and then making choices about which path to take. In order to have that kind of computational efficiency, you have to use very simple models. And those simple models don't capture the full complexity of what the robot can do. And so you really don't have the full capability of the hardware. You really are very limited by the simplicity of your reduced order models. They always say you want to make it as simple as possible, but not too simple. And I feel like in most cases, the model becomes too simple. So this is very early on, just after we founded Agility Robotics and just after we were getting some basic model-based controllers on these robots. And this is pretty simple. I mean, this is just a linear inverted pendulum, reduced order model. Now, I would say, as far as this technology goes, we have Boston Dynamics here. You guys have taken model-based control, I think, as far as it will likely ever go now, because RL approaches are going to supersede it. But, it took a lot of PhDs and a lot of engineering in order to get kind of the behaviors that we saw from them. This is what Agility was able to do with model-based control on these robots. But, we have new tools now. So this physical AI is this future of robot control. You don't need to be doing online optimization. You basically are doing the optimization offline, and you're compiling into just a forward policy. You don't have to be continually doing online optimization on the robot. It doesn't matter how nonlinear and weird it is. You can have a much, much higher fidelity model of the robot when you're doing the analysis to create your policy. And so that means you can really get into the corners of the dynamics and really utilize the hardware capabilities as much as possible. And once the pipeline is in place, once you actually have your everything ready, engineering is faster. So if you need to new policies and things like that, come on inside, guys. This is a super informal talk, and we can just sit in the front and come and go if you want. I won't be too offended. It's okay. Once the pipeline is in place, engineering is so much faster. Like, it's not a lot of time once you have your cost functions, once you have your RL pipeline, and then you put a brand new robot in it. It's like in a week, you've got policies that work really, really well. So that's pretty exciting. And then this is kind of the very first time we were able to be successful with RL policies. Come on in wherever you like to come and sit. The first time we were able to get RL-based policies on our robots and started to see some really, really, really good results. So you can compare this then to the model-based control that I showed you in the video a little bit ago. So another thing to keep in mind, I believe that this is the first dynamically balancing bipedal robot that was controlled using RL approaches. If anybody knows otherwise, if any other robot that was before this one, let me know, because I'd love to be able to make that claim. This is the first RL-based dynamic running robot. It was only 3 years ago. Now everybody can do it. So turns out it wasn't that hard. We just got lucky and happened to have the hardware that was capable of it. So anyway, clearly the future of control. So now, in general, what kind of AI, right? I just said AI. AI is a huge, big tent that covers lots of different techniques and different things. I'm seeing a few different kinds. I see this data-driven full coverage. I see motions from trajectories and then some stabilization around those trajectories. I call it an RL tunnel. And then policies actually across a workspace for kind of this whole body control. So I'll give a few examples of that. First is full coverage, right? So this usually works well when you're teleoperating a robot using the robot hardware so that you're collecting actually really, really directly relevant data of what that robot can do. And so that's how it does all this folding. I think of this, well, I'll talk about pros and cons. I think of this as like a trajectory library. So, if there's 10,000 hours of operation, then hey guys, feel free to come on in if you'd like. And it's okay if you get bored and want to leave too. So no worries. So conceptually, I think of this like a trajectory library, right? If you've got like 10,000 hours of operation, then I don't know how many, thousands of repetitions that you've got of motions. And you're basically recording all of those, and then you're kind of, saving that in a way that's accessible. And then when the perception system is looking at the scenario, it kind of takes a measure of the state of the system and then is able to kind of choose what's the right action to take from the full coverage of history that it's ever seen. And we do see some composition. So it's not like the whole trajectory has to be selected. It's more like bits of the trajectories. And so then we start to see some composition and some reordering, kind of like we start to see in large language models. And that's really promising. But what are the cons, right? I really liked, who was it that gave the talk about the force-based learning versus the vision-based learning yesterday? Polkett, thank you. I was forgetting his name. Yeah, the data to train these things just doesn't exist like it does for language or images. So you have to generate it, create it, make it up, invent it from somewhere. It doesn't exist anywhere. There's no internet scale piece of data. Your robot is unique. And that engineered system is nobody else has it, right? So generally the data we can generate is incomplete, low quality, and just doesn't give you what you need in order to actually do good manipulation in the world. So that's why you see things that don't require much force. You see things like towels. And all of those can be basically position trajectories, right? It doesn't take much force, so you can just follow a position trajectory. None of those things involve constraints with the surface and then having to really rely on those constraints. Certainly you can't control like a running robot using that approach. There's no good way to collect data or teleoperate for something that requires balance, for example. It's not really a dynamics policy. It's just a sort of position trajectories. So we see some good results, but there's clearly limitations on that. Okay, number two, motions from trajectories, right? And all of these are motion capture of a person, or like in the case of Disney, an animator writing down some interesting movements for it and things like that. And then you stabilize it in simulation in order to modify maybe that movement a little bit so that it works on your robot and so that your robot will basically do that movement. Yeah.
Hide the placeholder.
Oh, you guys see that too? I thought that was only on my screen. Well, what I can do here is if I optimize for video sharing, that goes away and then everybody online can see it better. Yeah, thank you for pointing that out. Yeah, so these little Disney robots are kind of my favorite. They're not a lot of degrees of freedom, right? Which is what makes it relatively straightforward, especially for all the animations that they have to have them, string them all together. And there's a guy with a controller pressing the different behavior buttons, like, do this behavior, do that bounce, things like that. All right. But you get the cool, some of these are the best dynamic motions we've seen by far, right? So that's one of the pros. They're really, really some beautiful motions and acrobatics and things like that. And maybe having 100 of these or 1,000 of these is a good path towards skill development where, you know, if you need to grasp something, you need to know how to open a door, any number of different things. You can imagine even just like having 100 of these for opening a door, and then kind of combine that with the previous one so that you select one of these, you know, trajectory tunnels, and now it's stable for forces in the world, perhaps. It just depends on how much of the RL you've been able to do. I don't know. But the cons in general is that it is just the one motion, right? You have the single motion capture behavior, and then you've stabilized around that one behavior. It's not a general policy. It can't do a lot of things. And so I think one of the real cons here is that people watching these videos, especially non-roboticists who are watching these videos, see the robots doing, you know, these kind of amazing behaviors, and they say, wow, imagine all it takes for a person to be able to do those things. I see a robot doing it, so I assume that the robot can do all of the things a person would have to do in order to be able to do that. And so it's just, of course, it's not lying. This is real. This is not a simulation. Those are the real robots doing it. But it does typically imply a lot more capability and behavior than is true for these things. So I would call that one of the cons. And the other thing is it just still has one of the classic robotics problem of how do you stitch all these behaviors together? And this has been around for decades, you know, trying to fit, you've got a controller, you've got a particular behavior, and how do you string all these behaviors together? And, you know, we've talked, my advisor, Al Rizzi, you know, with his advisor, Dan Kotacek, was doing this with classical controllers and calling them sequential composition, you know, and setting up, you know, a local controller that would get it to a certain state, and then the next controller setting up, take it to the next state, and carefully stitching these together. And that's still a problem that I don't think we know how to solve, and we don't know how to do that very elegantly. It sometimes gets really choppy. You can see it sometimes in videos of robots that do this with any of model-based control or otherwise. They have a behavior and then they switch discretely to some other behavior and they switch again. So figuring this doesn't solve that. It's unclear how to interact with the environment for grasping. So remember, this is still a trajectory-based thing that you're stabilizing. It's not taking in any information or data about the forces that you're applying on the world. Doesn't address that at all. And then number 3, I would call policies across the full workspace. This is something that Agility does, and I know a bunch of others do. I don't really know enough about, I looked at a bunch of videos from other companies, and I wasn't really sure what was going on under the hood. So that's the only reason I didn't show some of those videos. I know what's going on under the hood here. So I can say that these are just an RL-based whole body control with a full range of states. So digit under this whole body control, you know, we can lift cinder blocks with it. We can put the end effectors wherever we want in space. We can walk. Terrain. You can give the robot a huge shove, and it knows how, like I don't know, maybe it's a little bit of an extension of number 2, because instead of one trajectory, we've given it lots of inputs, not trajectories. So the benefits, you know, it's a general policy, right? It can work with a skill layer. So we can learn from demonstration or whatever, some behavior for the end effectors to do, and we don't have to worry about the whole rest of the robot. We just worry about a much, much smaller, easier to address problem to figure out some skills. And it kind of allows, I would call it the splitting of attention. Sometimes you care where your end effectors are, your hands. Sometimes you care about where your feet are, and you can make choices about what you're really paying attention to, and decide what the skill is that's important at any given time. The hard part, though, there's a lot of cost function engineering here. You know, the team is deciding how to tell it whether it's doing better or worse, and whether it's better performance or worse performance. And it's that gets well into the art versus science kind of question of how do you engineer these things really well. And one of the reasons that these guys are pretty good at it is because they also have a background in all the classical controls approaches, and so they've got a real background in the physics of it. But there's got to be a better way to train it. I don't know what it is though. Okay, so changing the topic a little bit, because the topic of this presentation is that locomotion and manipulation are not the same. So here I've tried for a lot of years to try to define locomotion, and I haven't really come up with a good a great definition of it, but I think I have at least an analogy where I feel that locomotion, walking and running, are one behavior, not two different behaviors, but they are a dynamical phenomenon. They're a self-stable kind of a special corner of physics and analogous to pendular dynamics. Now, way back, was it Galileo? I can't remember who it was that made the observation that when you swing a mass, the amplitude does not affect the frequency. And he sort of at the time, I think he was pretty old when he made that observation. He said, maybe someday this could be used for timekeeping or something like that. And then 100 years later, Christian Huygens wrote the equations for it and pointed out that it was actually a cycloidal pendulum like this, not a stick from a point. And then hundreds of years of engineering to develop escapements and a user interface with the clock face and a way to add energy to this without actually messing with the physics and all kinds of things like that. And interestingly, if you go to like the British Museum, they have hundreds of all these old escapements. All of the escapements, what they can do, you can imagine, how do you affect the pendulum without actually affecting its frequency? There's two places you can do it. Either when it arrives at zero velocity, so all of its energy is in potential energy, if you are able to instantaneously relocate the end of that to a new location and then release it again, it wouldn't affect the frequency. The other way to do it is when all of the energy is in velocity at the bottom, if you can give it an instantaneous impulse so that it changes its velocity instantaneously without changing its position, you can change its energy without affecting its timekeeping. And so all of the escapements are basically trying to figure out a way to give it the sharpest impulse at that lowest point. Now, I don't think that anybody has written down the kind of controls-based equations observation of how clocks work, but they figured this out, through hundreds of years of trial and error. So that's the same kind of question conceptually for legged locomotion, is how do we actually capture the self-stable dynamics and physics of this cyclic behavior and control it without messing with it. So you kind of want to steer the energy as it's going in order to really get the kind of fluid motion and behavior you want. Super hard. We'll probably, the same way that it did hundreds of years ago with a clock, without necessarily understanding everything about the physics of it, figured out how to do it with escapements. We have RL, and so we'll probably hammer away at it, figure it out, not really understand exactly why it's working until some scientist 100 years later does some interesting observations, but we'll figure it out sooner than that. I guess one other point I would say is all of the swing motions are very inertial. Like you can't have highly geared joints and be doing position-based stuff and have natural locomotion. You have to allow this kind of pendular swing of the body, the arms, the legs, and everything else. And you have to handle impacts really well with the ground. It's very hard to do. A lot of times the impacts are a lot of, jitter and slip and so on. And it really limits what we can do with these things. Manipulation is different. I think of manipulation as a series of statically stable cones, like not a cyclic behavior, but individual actions that bring the uncertainty of some manipulated object to zero. And I remember in grad school talking with Matt Mason a lot about this because he's just really well known for manipulation and very insightful. And he did things like drop an Allen wrench in a tray and then do a set of motions, and then exactly where the Allen wrench is and exactly what its orientation is. And so that was really important. It didn't take any sensing, it didn't take any perception, and it brought the uncertainty to zero with just a sequence of motions. And from his paper in 1985, it's been a while, the little example of when you pick up this pencil with a parallel jaw gripper, you may not know where the pencil is, but as soon as you close the gripper, now you do, right? And then my favorite example of this is one of the earliest humanoids, the Sarcos humanoid robot. It never walked. It didn't work that well, but it was a humanoid. And Chris Atkinson had one, and he was juggling with it. Now, when you imagine you throw a ball in the air, the uncertainty kind of grows with time as the ball is going through this ballistic trajectory. And now when you grab it, you need to bring that uncertainty to zero. And so conceptually, this is like a cone, a cone of space. And what he did is just put literal cones on there. So the ball is somewhere in the stability region of the grasp, in this case, a cone, and then the ball lands down at the bottom of this cone, and now the uncertainty is back to zero. So it's a direct literal representation of this concept. We use it a lot in woodworking too. I make furniture just for fun on the side, And it sort of surprised me. I started by using CNC machines and milling machines and things like that in college when I was building robot parts. And that's, you dial it into a thousandth of an inch and you measure things with a caliper, and that's how you get your precision. But in woodworking, it's not at all. You put things, you put 2 or 3 different pieces of wood up against a jig, you slide it through the cut at the same time, and you know that they're going to fit perfectly just because you're using kind of jigs and references. You don't know how many inches it is, you just know that it will fit. And I think that is much, much more analogous to how people manipulate the world and do things. So, I imagine we need to be thinking about how do we build manipulators that enable this, and this is how we would design cost functions as we're trying to figure out how to control manipulators. We want to do dynamics randomization on all the different locations a thing can be and find the grasps that are most stable for when they do the motion, they bring the object to 0 uncertainty. Yeah.
Yeah, when you mean cones, the
Yeah.
rotation,
Yeah.
trying to refer to like friction cones kind of stuff?
Not friction cones. No, it's a good question. So I mean more like a stability region. So I don't know, what's an example? Well, okay, the gripper with the pencil, right? If the pencil's over here and the gripper's over here, it's not going to work. But anywhere within this region is kind of the open side of the cone for that gripper. And then when you close it, it brings it to a point, and that's the bottom of that cone. So it's like the stability region for that individual action's capability. Yeah, and then because it's an action and not a cycle, that's different from the stability regions of a cyclical system like a locomotion, or even the sequential composition concepts from earlier robotics. Thank you for the question. So different tools, right, for different things. This is a video from years ago. When we were first doing this, RL is just great for locomotion because really you only need a model of the robot. You don't need much about the model of the world. And it can be very robust to the kinds of disturbances you're going to see in the world. We don't care very much if the ground stiffness changes because the leg stiffness is so much softer that even if the ground stiffness changes by a factor of 2, it only changes the overall stiffness to the center of mass of the robot by like a few percent, right? As an example of why that's so robust. And when it's going up and down stairs, this is very much a force-based behavior. It's not position-based. So at some point, the robot says, I want my foot on the ground. I'm going to apply some force. It'll just extend the leg and it'll hit the ground wherever the ground is. And it doesn't take that much time to change, whether it's closer or farther, and it still applies that force, which is why you get such robustness, even though the ground height might change quite a lot. Also, we know what the physics look like. We can write cost functions. We understand this problem really, really well. And kind of a little side point is that the velocity is a really good optimization signal because every millisecond, when you're measuring it, you can measure your velocity and you can adjust a little bit to maintain that velocity. If we instead have a position like I want to be on the other side of that room, it's much harder to have a good reward function for that when you're using reinforcement learning. So we were successful much earlier for walking and running behaviors that were velocity based. It was much harder when we cared about the XYZ coordinates of the end effector and wanted the whole robot to be in a certain position and not just a velocity. My favorite video, part of this video, I'll skip to it. This is when we were just totally shocked at the stability of this thing. The toe catches right on the edge on this next step here, I think, and starts to fall backwards. And then it doesn't care, it just starts to fall and then keeps going. I mean, we didn't program that, that just emerged. So we see this kind of behavior. This is, at the time, it was super exciting. Now, this is common. So I don't know, that's exciting in and of itself. I think that learning from demonstration seems like the best path for manipulation because you're not going to use successfully reinforcement learning to explore the full range of the elbow up, elbow down, all the kinematics of the entire workspace of what you're trying to achieve. You have to give it some hints, a starting point. This is where kind of like that RL tunnels, is why that seems like it might apply here because you give it a hint of here's how you pick up a cup, here's how you open a door. And then it can explore in that region kind of around that. in order to find it. So the other piece of this is that learning from demonstration means the human is able to give a lot of context about the world and about the environment and about the space around it. And you actually need that for manipulation. Still, once you kind of know the region, you know what your grasp is, you know what you're grasping, now you can do that concept we just talked about, which is the stability cone and bringing that uncertainty to zero with the, the strategy around your grasp. But you do have to get it kind of into the right region first. And so I'll kind of end there. This isn't like detailed answers. It's a kind of high level, just my philosophy around AI and control. I think AI is a hierarchy. Certainly there's no silver bullet. And I don't believe in end-to-end pixels to actions black boxes. I believe that there are many tools. Engineers need to understand what those tools are good for and apply them in the right place. And then you can build things faster and more effectively with these tools, but you're still going to take engineering. It's not going to be a magic thing. So I think of a hierarchy like this, and we imagine that that hierarchy is based on how fast things move. So at 2 kilohertz, it's a different tool than at 1 hertz. And then it's also the amount of information and context about the environment that you need. So if you're really thinking about what should I do in this factory, you need to have an awful lot of context and human context that can really only come from data and large language models and things like that. And perception, that kind of requires all of that. But at the fastest level of what happens at contact, at impact, the hardware reigns supreme. The hardware is the thing that has to be special, has to be exceptional. And then that is in a very holistic design with your RL approach based on understanding the physics of what you're trying to do. And that has to happen really, really super fast. And so at the bottom there, I have hardware design and GOFE. That's from Ken Goldberg. It's a good old-fashioned engineering. There's really no way to just have an AI system spit out a CAD model for your robot. You're going to have to know what you're building and why you're building it to start with. And then, it's more specific, of course, at the very bottom, and it gets gradually more general as you go up this stack. So these language models could work on many different types of robots, doesn't matter. But the RL design for your robot is going to be unique for your robot. So, okay, thank you. That's the end of my talk. This is just a video, a little bit of what we're doing right now, which is we've given it a few hundred examples of grasping and manipulating these boxes, and then started doing this learning from demonstration policies, which again are fairly focused on top of the whole body control, which is something that we did reinforcement learned. Your question?
Question. For something like hardware, you talked about hardware.
Yeah.
I want to know in your thoughts on how policies adapt when hardware changes through reliability events. Because I think that's something that a lot of even companies out here, they're like, there's no guideline for like what a rel suite is, but as motors wear, you'll have like different backlash in the system and the system dynamics will change. So how do you propose like policies adapt to fit the hardware changes?
Sure. Well, I think, when you're doing reinforcement learning for really the low level control, you really have to start in simulation just to get enough hours on the thing. And you can get really close and it'll work on most of these robots. But really to get that last 20 or even 30% of behavior, you have to learn in real life. You have to have kind of stochastic things that you're always trying and always refining. And I think that'll fit right into every hardware is a little bit different. Hardware changes over time. Once we really know how to do this reinforcement learning in real life, that's the same kind of thing. I know I'm old now, and so I've had to do a lot of reinforcement learning in real life to pay attention to how my body has shifted, gotten slower and everything else, and easier to injure, and then change my behaviors quite a lot. Robots, I'm sure, will have to do the same thing. That's good. Anybody else? Questions? Yeah.
Just think about the large behavior model. Do you think it's a good solution for solving the issue?
I mean, I think truthfully, I don't know enough about it in depth to have a really strong opinion. I think that they are using a lot of the same tools that we are, but maybe not all of them.
Data collecting,
Mhm.
they use it to train the robot, and also they probably with the DI to integrate large behavior model on Atlas.
Yeah.
And not similar, but they use Plenty of data.
I mean, I believe that that's basically a demonstration. And I don't know how much I think you're going to need a base to really do dynamic behavior that you will not get from demonstration. So the large behavior model, again, I don't know enough about this to really go in depth, but I believe it's kind of a range of skills that you would be able to do, kind of like a, you know, not just one skill from learning from demonstration, but a big range of them. And that seems very useful to me. Good. Yeah.
Can you comment on the speed of execution? Because now
Sure.
it's of course a static motion.
Yeah,
Are you trying to speed it up? And
sure.
do you see the
So that's not really static at all. Like if we did turn off power, the robot would collapse. It's balancing.
instead of snatching on it, right?
Yeah, there's not a lot of ballistics going on. There's not. That just comes with time. Yeah, this is still as slow, jittery. We don't really know how to do learning from demonstration really, really well yet, I don't think. And I think also once you do learn from demonstration, now again, you're in the vicinity, but you're going to have to do RL to really do it well. And we're back to the problem with manipulation where we don't know how to write the cost functions for it, or engineers would have to write the cost function for every individual skill or something. And I don't think anybody knows how to do that in an automated way yet. The analogy for like how you learn to play the violin and the teacher shows you how to do it, that's learned from demonstration. But now people are very, very good at knowing what the goal is, knowing what the sound should be, and then finding the right paths of exploration to try things until they've practiced and do it really, really well. And RL is so much less focused than that. However many millions of cycles it has to go through and try everything in RL right now, it's much less able to just focus in on going towards the goal. I think that's the trick for this community. Good question. Yeah.
Yeah, well, question is, so I think learning from demonstrations and combining with RL or whatever robotic control has seemed very powerful. But we also mentioned that demonstration from position based is very inherently limited to simple tasks. And you also mentioned thinking about dynamics and also contact groups is important. Do you have any insights of how to jump from position?
Yeah. Okay. Good question. So it reminded me of an analogy. I showed at the very beginning, the limitations of a model-based controller and how it's kind of stiff. Well, this is learned from teleoperation, right? So we've got the VR goggles on and then teleoperate the robot to pick this thing up. And then those are the examples we use. And it works because it's on top of a whole body controller that we've already learned so that it can lift heavy things and it won't fall and all of that. But still, all of the data and examples we've given it look like that. They're fairly slow. I think the way that we have to do it now is analogous to the number 2 with, the trajectory tunnels where, we've got like a behavior. We should be able to have that as a starting point and then do some RL approach, some sort of learning where the robot needs to explore on its own to get to the corners of the robot dynamics and not, if you think about the Venn diagram of all the behaviors the robot can do in one circle, and then all the behaviors that a person controlling the robot can do in another circle, you've got this very, very small overlap. And that's what we see right here is that tiny overlap of what a person controlling the robot can do. We have to find a way for the robot to play and explore a little bit in order to actually get to do these fast things. We don't know how to do that. I don't know how to do that. All we know how to do is cost function engineering, which takes a lot of time and energy and expertise from people and trial and error to get a certain set of behaviors done. There's got to be a better way to do it where you have ChatGPT tell you whether this is good or bad or getting better or worse and automatically annotate a whole set of videos and let it explore somehow that way. But I don't know yet. I think the community will start to figure this out in the next couple of years because everybody's looking at it.
Cool.
Thanks.
I think we're running out of time. Let's thank our speaker again.
All right.
I think it's a good segue. I think someone asked about large behavior models, and I think it's a good segue to our next speaker, Benjamin Birchfield.
Hi, Ben.
He's going to talk about large behavior models for robot manipulation, what works and what matters. Yes.